Okay, hello everyone. Can you hear me? Okay, can you hear me well? Okay. So, hi everyone. Good to have you all back and maybe some new ones. Again, this is another one in this sequence of informal webinars. Maybe one can title them, Start at Home. Sorry about that. For some reason, I need to. I don't know why, but I thought that I muted my phone. I'm sorry about that. Let me just mute it again. Okay, I don't know what's going on here, but I will just. Sorry about that. For some reason, my phone wasn't muted. Okay, apologies. Okay, so this is another in the sequence of lectures that is supposed to. Oh, can you hear me? Audio is off. Can you guys hear me? Okay. So, Bernard, I think your audio is off. Okay, I was just looking at the, getting more interactive as time goes by. So this is yet another informal webinar, and I apologize for all this sort of setup. I'm going to screen share as I usually do. So whoever cannot hear Guilam, I think it might be a problem on your side because others do seem to hear. So I saw that Bernard and Guilam say that they cannot hear. Wait, do I need to click the unmute button? Okay, good. So it seems that the problem is not on my side. Anyone who cannot hear should probably be clicking on the unmute button. So, as I usually do, I'm going to screen share, and I will, from time to time, go back and check in on some comments and questions, and we'll have several parts here. So the general topic of today's talk is about how to write programs using polynomials. And for some folks that might be new here, maybe you're asking, why would we want to do this? Right? Why on earth would we want to even use polynomials to write programs? Why not just write programs in whatever it is, in assembly or C++ or your favorite language? And the answer is that, lo and behold, that's how you get succinct proofs of computational integrity. So for reasons that we talked a little bit about in the past lectures, so this is succinct. For reasons that we talked about briefly in previous lectures, and those who are new here are welcome to go and watch those videos or see other links. It turns out that if you want to create proofs of computational integrity that are very succinct, in which checking them is logarithmic, and if you want things that are with zero knowledge, then the best way, the most efficient way we know to get these things is to go through polynomials. And I spoke a bit about the mystery of why polynomials. They have all these beautiful properties about being good error-correcting codes and being closed under multiplication. Their sort of degree doesn't go up too much. So they have a lot of beautiful properties. And that's not the topic of today's talk. Today I want to sort of move on and just say, suppose you, for this weird reason, really want to write things as polynomials. So how would you go about doing this? And that's the topic of today's talk. And first of all, we need to think a little bit about what do we mean by computation. So what's a computation? What do we mean by that? And in general, we think of some fixed transformation, right? That takes us from, we have some input, and then we have some weird thing called the computation. And then we feed the input into it, and out comes the output. So this is a very generic thing. I just want to say that there are two very basic ways to think of a computation, and we'll look a little bit about at each one of them. So one is as a circuit. So what do we mean by a circuit? It is something that has inputs, maybe something like, x1 up to xn go into the circuit, and then maybe we take two gates and we add them up, and maybe we take two other gates and compute the AND of them, and then we take this and this and we do whatever the OR of it, and maybe that's our output. And of course, typically circuits have thousands or millions or billions of these gates, and they could have many outputs, not just one or two, but they could have many outputs. The point is that we sort of linearly in one linear path go from the inputs to the outputs, and basically we go through this computation. So it's a fixed computation, it's a circuit. That's one natural way to think of a computation. The other natural way to think of it is as a program, and that's a little bit more mysterious. What do we mean by a program? And I want to now give the sort of way that I think that is correct to think about what a program is. So basically, we have a state of we have states. We have a state of states. And we have, so this is states before a step. And we have a set of states after the step. And then a program is some relation that is basically, some subset of the set of states that come as input and the set of states that come as an output. So what do we mean? We mean a computation is something that sort of progresses locally. So you have a bunch, let's say, of registers and some context of the memory. So these are maybe your registers. And then here you have your memory. This could be your RAM. And basically, so this is at time t. And then at time t plus 1, you're supposed to move to a new set of registers. These are new registers, and maybe you modify your RAM. And the point is that there's some transitions are legitimate, and some transitions are not legitimate, depending on, one of these registers, for instance, could be your program counter. So if your program counter is now indicating a number that says that you should take this cell and let's say add them up and then store it in memory and in this location, then there's really based on fixing whatever is the set of values in your registers and in your RAM, there's really just one legitimate relation after that, which is the only legitimate thing will be the state that looks exactly the same as this. But for the change, that what you have in this, in this cell is the sum of, these two entries, and everything else must be the same. So that's an example of one of the transitions that your program allows. A different transition that is more open-ended might be that you're now loading a new input from some from some keyboard or something, and then basically your program counter has a value that indicates that now you're supposed to accept any possible thing into this cell. And then if you look, what are the legitimate states that you can move to? Well, everything stays the same, but here you could basically have anything you want, right? So program, just to summarize this, a program, you can think of it as some binary relation. Binary means that it takes two values. Binary relation just means that it's a subset of all possible sets. Binary relation on basically on pairs of states. And if you think about it, if you write a program, let's say in Python or C, it is then compiled into a set of instructions, and that set of instructions sort of specifies what the relation would look like and what the state space would look like, and what are legitimate states, and so on and so forth. So just to summarize this part, computation, and notice that so far we have not mentioned on this slide, we have not mentioned the word polynomial. We have not mentioned the word finite field or any algebra. This is very, this is something that you could think of as a hardware gadget, built into silica. And this is good old programming, maybe explained in a slightly different way, but it is completely computational and has no algebraic interpretation. So I'll jump back and just ask whether there are any questions so far just about this very preliminary presentation of any questions so far? Can you hear me? Okay, I see there's one question. Okay. Why would functions not work? And why do we need relations? Okay, very good question, Soham. So often when you learn about computability or computer programs, you learn about something called the transition function. A function is something that for every input has exactly one output. So essentially, if you're in a certain state, transition function would tell you that you can move to one and only one new state, right? So the question is, why do we want to talk about a transition relation, which allows you to move from one state to possibly different states? And the answer is that in certain cases, we want to allow the user, or we want to allow the program to move from a current state to several different states. And one way to think of this is, suppose we need an input, a number between 1 and 10. And really the program would like to get a number between 1 and 10 for it to operate. So a view that is perfectly consistent with what's happening is to say we are now in a certain state, and from this state we are allowed to move to one of 10 different states, one corresponding to each one of the possible inputs that we allow. Okay, now you could also move to the view of transition functions and say, given a sequence of inputs that we can sort of guess in advance, this is like part of the description of how the function works, and you're supposed to get that. That's perfectly fine, but I personally prefer to think about it as a transition relation. Okay. So are stack machines also valid models? Yes, definitely. So all these different machines, so stack machines, pointer machines, RAMs, Turing machines, they're all essentially equivalent in one way. If you have enough stacks or enough depth of them and so on, you can sort of argue even formally that they're equivalent to one another. Yes, so you can definitely have different models of computation, but I'll focus here just concretely on two very simple models that are pretty generic. Okay, so now I'll jump back to the board, and let's talk about what things look like when we think about these algebraically. So just one second. Let's use a different color. So oops. Try to draw a line here and talk a little bit about how we think about. So here we'll have circuits, and we'll think a little bit about algebraic circuits. And here we'll think about things like algebraic machines. Let's start with circuits because they're simpler. So when we have silica circuits or right that we build chips with, we usually use things like a Nand gate. And a Nand gate is this one type of gate that you can from it derive anything you want. You can derive an OR gate. You can take a bunch of Nands and devise from them a XOR gate. You can get an AND gate and so on and so forth. You can get a negation. They're like really, really good. So you just need this one gate, and that's enough. And then in the algebraic world, there's one type of gate or constraint that is sufficient for getting all the other kinds of constraints that you want. And you can basically take any circuit and any computation that you would like to do. If you want to take basically, if you have a bunch of inputs, if you have any function that goes from a field, so let's say a prime field, but it doesn't really need to be a prime field of, if you take n inputs and you really want to go to some field with, want to take n inputs and get out m inputs for any nmm, there exists a circuit in which all gates are, and here I'll fill them in, I'll call them rank 1 quadratic constraints systems, R1CS, which computes the function f. So what is an example of an R1CS gate? So first of all, we need to think about wires. So we define the number of wires that we need. And let's call them, W1 up to W maybe big N. So you basically are going to have, you're going to fix the number of wires. And then a constraint or a gate always, so the analog of a NAND gate is something of the form, so like the jth gate, and you can have many gates, but all gates look something like this. You take some linear combination of the wires, you give them various coefficients, so summation AI WI, and you take that, you multiply it by some other linear combination of the wires, you subtract some third linear combination of the wires, and maybe some constant D as well. So in all of these, you should number them by J. So the jth constraint is basically, or the jth gate is defined by, these sequences of vectors, where all of these AIJs and BIJs and CIJs and DJ, all of them, these are fixed constants from your field, some prime field. So just to give you an example, okay, suppose you want to take wires number and two, suppose you want to take wires 1 and 2 and do a multiplication, multiply them. So what would you do? So if you want to do a multiplication gate of let's say wires 1 and 2, you could just have basically A1 equals 1, all the rest equals 0, A2 blah 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 to AN equals 0. And then you'll have, B2 equals 1, everything else, B1, B3, so on and so forth equals 0. And now everything else, the C's all equal zeros, all CI equals 0. And what you really get is wire 1 times wire 2. And maybe we want to make that equal to wire 3. So maybe we'll make we'll make C3 equals 1, and then all the other C1, C2, C4, so on, all of them equal 0. So now what we really have is that the product of W1 and W2 goes into what W3, which actually means that you have this multiplication gate that takes wire number 1, takes wire number 2, and out comes wire number 3. Okay, so this is an example of a gate. And similarly, you can also get addition gates, right? You could make this, you could use the constants and fix certain wires so that basically you get an addition gate or a subtraction gate, and you can have constants here. So this one type of gate, it's called rank 1. So R1CS means rank 1 constraint system. This one type of gate is enough to basically take any arithmetic circuit and create from it a bunch of constraints that each one of them, you think about it, is really just a polynomial, right? It's a polynomial in it's a polynomial in the variables W1 up to W big N. So these are variables. And it is a polynomial of degree, really of degree 2. It is linear. These A guys makes this, this part is sort of a linear polynomial, right? This is a degree 1 polynomial. You multiply it by another degree 1 polynomial, and you subtract another degree 1 polynomial. The total degree of this expression is a degree 2 polynomial. So basically what we have done, just to summarize, what we've done here is that we have a way. Let me just sort of continue this line and just say that, so we have a way to convert any circuit, which means, something with wires, multiplication gates, addition gates, and write it using what? So we're using, let me just say, if we have S many gates, that's the number of gates, or let's say that if S equals the number of gates in our circuit, then we get some polynomials, let's call them, Q1 up to QS. And each one of these polynomials belongs to what? It is a polynomial whose coefficients come from our field. It is in the variables W1 up to W big N. Those are the variables. And it is of degree less than equal to 2, right? So this just means that each QI has a certain form, but actually these are not even generic degree 2 polynomial or quadratics. They can be written, you can think of them, they are a rank 1 quadratic system, which is something I prefer not to go into. But we can basically take any circuit and write it as a bunch of constraints. Each constraint is a polynomial over the wires of the circuit. So just to summarize what has gone on here, I'm saying that one popular way, and again, these things are called, R1CS constraints. And they're very popular, when you look at things like snarks. For instance, if you go to the Zcash and you look at the circuit there, you'll see a lot of discussion of R1CS constraints. They're also used in other systems. They're used in things also like Aurora, and they're used in Fractal. They're used, I believe, in bullet proofs. and other systems as well. So, and one of the reasons they're very useful is just like, it's a little bit just like the Nand gates above, right? You can take anything, any computation that you care about and express it using Nand gates. Now, it doesn't mean that you can't do it using OR gates or a combination. I mean, you can express it using, 2 of these 4 other gates. That would also work. So you don't necessarily need to work with NANDs. But NANDs are very useful because in Silica they're implemented very easily, and it's very convenient to work with them. So similar thing is happening, or has happened with R1CS. You can work with other kinds of constraints, but it's very convenient to work with R1CS. And by now, there's a bunch of libraries out there that allow you to convert various computations into R1CS constraints, sort of compile them into them, and so on. Now, before I finish with the circuit description, I just want to point out that you can, if you want to work with R1CS constraints, you can do a lot more than just writing circuits, because you can have all kinds of constraints that are not necessarily, are not necessarily thought of mentally as part of a circuit, as we described, let's say, here, right? It's not necessarily that we always think of the constraints that we write with R1CS as things that necessarily go into a circuit. For instance, we could think of some constraint that just means that a certain input must be a Boolean value, right? Take either 0 or 1. And we might think of that as a type checking constraint that we throw onto, let's say, W2. We want W2 to enter this kind of multiplication, but we also want, in addition, to make sure that W2 is either 0 or 1. So we want to write something like, we would like to add something that says, basically W1 times 1 minus W1. We would like to write this kind of constraint, right? That this equals 0. This is a Booleanity constraint, and we discussed this kind of constraints in the past. So you can do more with R1CS constraints. You don't necessarily just need to build circuits, but they're convenient. Okay, so now I'm going to go back and ask if there are questions about this thing. Yes, and please, as I'm speaking, if something is not clear, then you can just go ahead even before I ask and just write the questions, because then we have this list of questions that I can go over. Okay, the first question, can you explain how equality and less than gates work? Okay, I'm guessing that you mean, okay, these are 2 different things. Equality constraints would just have you, you can take an R1CS constraint that basically sort of fixes the B value to be 1, and then has just the A value minus, the C value, and then you get an equality constraint. So that's how you get equality. Equality is simple. Now, the less than constraint points to a very interesting problem that we have to deal with. So when we think about a less than constraint, we assume already a natural order on integers. So we're already assuming that we're working in this universe where there is an order on all the elements, and actually these elements go up to infinity, right? So, the integers. Now, when we want to get succinct zero-knowledge proofs, we actually move to these other universes that work over finite fields. The simplest of these finite fields are integers modulo a prime. But once you, and that's the simplest of the cases, there are more complicated cases. But even in this simplest of cases, you lose all notion of, smaller than. There is no order. It's basically cyclic, right? That if you get to p minus 1 and then do plus 1, you're back at 0. So this is a special case of this more general problem that we often want to take a computation that makes a lot of sense to us in the real world, like integer operations, and then argue about them in this other universe that just doesn't have integer operations. And then to answer the question, basically you have to go through a pretty elaborate process that will take your element, right? You want to compare two elements, A and B. Now, these elements, naturally in the world where they reside, they are just field elements in this weird field where you have wraparounds, right? So there's no notion, right? One is not smaller than two if you're working modulo 5, right? They're just incomparable. There's no way to order them, no natural way to do it. So what you would do is you would take your objects that you want to think of them as, integer typed, and you would somehow break them up into, the simplest way is to break them up into bits, right? Sequences of 0, 1s in the natural way. And now you save each one of these, integers, you save them as a sequence of their bits. Each one of these bits is now a field element. It's either 0 or 1. That's where a Booleanity constraint might come in. And now you work with basically Boolean gates to sort of, just check by in a way that is very similar to how you would use a bunch of nands or ors and ands in the Boolean world to check that A is smaller than B. So that's what you do. You sort of move to the Boolean world, and then you simulate the Boolean world using 0s and 1s and then multiplication and addition gates. And of course, this is a very inefficient process. You want to do it more efficiently. Okay, next question. The rank 1 quadratic systems, are rank 1 quadratic systems a subset of rank 1 constraint systems? Well, it's the other way around. So when you have a quadratic system, right, one way to write a quadratic system is to think about, to write it as W transposed times a matrix M times W, right? Whenever you have that sort of expression, you get a quadratic. Now, when we talk about rank 1 quadratic systems, what we mean is that the matrix M in this quadratic expression must be a rank 1 system. Now, you could talk about higher dimensional tensors, which would give you higher degree, but no one's doing it these days. And then, this is related to, I don't want to go there. So to answer your question, usually the right way to think of it is that rank 1 quadratic constraint systems are a special case of general quadratic forms in which the matrix M, by which you multiply W, your vector of indeterminates from left and right, happens to be a rank 1 constraint system. Okay, next question. If the circuit is uniform, short description, then do the resulting polynomials Q1 up to QS also have a short description? Okay, this is a terrific question. The short answer is yes. You can take a succinct circuit, meaning a circuit that sort of is repeated many, many times. And if you think about it, that's really what what a program looks like, right? You have this very succinct representation that is repeated many, many times. And you can sort of have short descriptions in certain cases, actually in all cases, but in some crypto systems, it makes sense to write them this way, and the verifier actually can reap the benefit of this succinctness, and in other systems, you can't really utilize this. So even for, and what I mean concretely, so if you go to the paper called Succinct Aurora, but I forgot what its formal title is, I can share the link about it. Later, there is a specific discussion of how do you get succinct R1CS systems and how do you construct them and how do you argue about them, okay? And that works very well in the sort of Stark setting. So the Succinct Aurora paper gives you a special case of the Stark, and it's very useful. If you would want to build a snark from it, a pre-processing snark with the trusted setup and so on, you could still have uniform circuits, but really sort of the trusted setup would still have to be very elaborate and sort of unroll the circuit, and you don't reap the benefits of it. Okay, next question. Is Q1 up to QS? In Q1 up to QS, is S the number of all gates or only multiplication gates? So the answer it is the number of all gates, but sort of a single R1CS constraint can sort of bring into it, basically you can take one linear combination multiply it by another linear combination, and subtract another linear combination. So in particular, you can just get linear combinations out of it. You can take just multiplications if you want, but the most efficient form, and this is because this is what the sort of cryptography and the proof systems allow you, the most efficient form is sort of to, take your computation and make it look like, let's have this one gate that actually takes a large number of inputs, has some arbitrary linear combination on them, multiplies it by some other large linear combination of other inputs, multiplies these two and subtracts a third linear combination. So you can get more mileage out of that. That becomes more efficient. Okay, can you explain the diagram where you use W1 and W2 as the input to the multiplication, which then outputs W3 more? The algebraic form did subtraction. Sounds didn't get that transformation. Let me maybe jump back just to show the explanation. So what we would want to do, let me just right. Okay, so what we want to do here is we would like to enforce W3 to be the product of W1 and W2. So we would like W1 times W2 minus W3 to equal 0. In general, when writing constraints in the algebraic world, it's always good to think of true as equaling 0. So we often sort of just completely neglect this equal 0 part, and we just say the constraint is that W1 times W2 minus W3 is the constraint, but we implicitly mean this thing equals 0, and we just sort of just don't write the equal 0 part because it always is there. So I think this should explain and answer that question. Okay. Next question. Is it, for example, for zero-knowledge protocols, better to have a combination of many 2-input, 1-output gates, or to have just a few, let's say, 5-input, 2-input gates or so? So the answer is very simple. You want the circuit that computes the functionality you care about and does so using the minimal number of R1CS constraints. That's the most efficient. So if you can take 20 different inputs, sum them up, multiply it by 100 different inputs, that do that multiplication, and you can make more headway and have a smaller number S of constraints, you're better off. And this is an optimization technique that a lot of people, let's say, in the who build the snarks, let's say at Zcash, have mastered to a high degree of perfection. And sadly, I'm not one of them, so I know the general theory, but these sort of this expertise is not something that I can say much about. Fixing a typo in my previous question, the algebraic form did subtraction, but it didn't get the transformation on how that becomes the output wire. Okay, so the way you should think about it is that we would like to enforce the output wire to get a certain value, and that value should be the multiplication of the product of these two things. So we ask the prover, please, prover, make sure that you assign values to the wires in some way, however you want, but be sure to make it so that if you take W1, multiply it by W2, subtract W3, that thing will be equal 0. And the only way to do it is to actually have W3 equal the product of W1 and W2, right? So you're putting a constraint that the prover must satisfy. If the prover is honest and actually wants to run the circuit as intended, then he can do it. But if he's trying to cheat, then this is a constraint that will not be satisfied. So we take a gate and construct a constraint from it. But you can take your constraints and make them more general, as we said, like Booleanity, type checking, and things like that. Okay, thanks. Great questions. So now I want to go back, and I would like to go to the other side, which I'm more sort of interested in for obvious reasons. This is the way we sort of argue when we build Starks. So here I want to explain, how we go about building these things and generating these relations. So we think of a computation, and we think of a computation that's going to be very long. So we think it's going to take, t steps, and t steps, and t is something really large. Maybe, I don't know, 10 to the 9. So like 1 billion steps of computation. So it's some really large computation. But then we sort of look at two states in it. And we ask ourselves, so we have a bunch of, let's say, registers. And you'll excuse me, but in this talk, I'm just going to completely wave my hands on memory. Maybe if we have time at the end, I'll say a few words on how we deal with random access to memory. But let's suppose we just have this computation that we care about here. Now, one thing we could do, but we won't, is sort of just open it up into a big long circuit of size t, and then we have, you could, of course, take the transition relation, how you go from one state to the next state, and you sort of can open up into a circuit. But we're not going to go down that route. What we do is we, first of all, write a bunch of constraints such that, so we write, any set of polynomials over the variables. I'll call them, let's call it the current state is, denoted by the x variables. And then the next state is the y variables. And I'll actually allow myself even some auxiliary variable z. So this is, the current state. These are the registers I have right now. These are the variables representing the state in the next step. And these are auxiliary. And I'll show you in a minute how this could be useful. So I just want to write any set of constraints such that, so these polynomials, I'll also call them, Q1 up to Qs. And these polynomials, what are they? They are polynomials coming from, again, from the field that we're working over. They are in the variables x, y, and z. And we can allow arbitrary degree. We would like it to be small. So think of d as small, but d can also, d could be 2, it could be 3, it could be 5 or 10. We will pay as the degree goes larger, but these could be any polynomials. They don't have to be rank 1 quadratic constraints. So we just want to write a bunch of polynomials such that a pair of states, x, y, belongs to the relation that we care about, the relation of the computation, if and only if there exists some vector of z variables such that all of the polynomials are satisfied. So Q1 of x, y, and z equals all of them up to the very last one, Qx, s of x, y, and z, all of them equal 0, which again means that we think of this as saying all of the constraints are satisfied. And so let's see the differences between and we call these things this is part, it's not the whole thing, but this is part of what we call this wait, I'll just move this down. So we talk about this thing and call it we call this an algebraic intermediate representation, or for short, AIR. So intermediate representations are very important topics in programming languages and compilers. And here we have an algebraic version of an intermediate representation of a program. The program takes the transition relation and finds some set of polynomials, an arbitrary set of polynomials of low degree with the smallest number of variables and the smallest degrees and so on and so forth. But you're allowed anything you want. It's just that you'll pay in the complexity of the start with it. And then you write these down, and you want to make sure that they capture the program. So if you look at sort of air versus R1CS, so like there are a number of things that jump up. First of all, let me just write some of them. No, that's not what I wanted. R1CS. Sorry. And I don't know. So let's just have a few comparisons. I hope this will work. I don't know how many I need, but anyways. So here we have degree 2 and even rank 1. Whereas here we have arbitrary degree D polynomials for any D. Here we unroll the circuit, even though, as I said, you can talk about succinct versions of this, but that's another level of complication. Whereas here we you do not unroll. You basically convert the computation. You do not unroll computation. You take the transition function, which you could think of it as your C code or whatever it is, and you find a way to express it. Yeah, I think those are the main differences that I can think of right now. So here, the size of the system is as large as t, as the size, which is the size of the computation. If you're looking at the computation that takes t steps, and here the size of the system is as large as the size of the program describing it. And often the program is much shorter than the, sorry, this should be describing it. Yeah, sorry. So the next thing I want to do is talk about how you take these errors and then you make them succinct over larger domains of size t. But let me just stop here and ask a little bit about for questions. So any questions on the general comparison of errors to R1CS? Or okay, what do you mean by unrolling the computation, the circuit of a computation? Okay, suppose the computation you care about. So, for instance, at Starkware, we're gonna our first product is a scalability engine that basically allows an exchange to prove via a succinct proof that it has processed correctly a large batch of trades and updated a state of a system, and now the new Merkle root is something new. So the Merkle root state was A, and it was a Merkle root of a big tree of accounts, and the accounts had all kinds of assets and values. Now you're going to move to state B, and you want to prove that you moved correctly from A to B. And let's suppose, and the number of trades that you're settling and the number of transactions that have transpired is some number that could vary. Like one batch it could be 100, another batch it could be 100,000. Okay. So if you wanted to do this with a good old R1CS system, you would either unroll the largest circuit, or maybe, which basically goes over these, let's say 100,000 transactions, and sort of, right, you could imagine a circuit that basically goes over that is the unrolling. I mean, okay, first of all, what does the program say? The program says, you get your input, which is the number of trades that are settled. And then, you have this loop, something that says, right, for I, smaller than this, the size of the batch, you start something. Now, for each instance of this something, right, for each settlement, you do a bunch of things. You update the accounts there, you check a bunch of signatures, you update the amounts, Okay, that's a succinct program. But you could unroll it and say, oh, the number actually is 100,000, so I need 100,000 iterations of this transition relation, and each one of these steps is actually a circuit. That's unrolling the computation. So in an R1CS setting, you would do that. Probably if you want to work with different batch sizes, you would have maybe different systems, one for, for every power of 2, for 128, 256, and so on and so forth. And you would sort of go to the right circuit, but you can't really argue with them all at once easily. Okay, so that's what we mean by unrolling a circuit or a computation. If you're using an error to express a long computation for proving in a Stark, doesn't the proof still end up depending on the length of the computation since the trace is much longer? Most certainly, yes, right? Someone, and it is the prover, someone has to run the computation, right? And if the computation is 100,000 transactions, someone has to unroll those 100,000 transactions and process each and every one of them. Otherwise, we'd be in big trouble. But what we want to save, and an error allows us to do this, is the verifier side from needing to run a computation ever that is as long as the size of this batch, or trusting anyone to do any sort of computation that is linear in that amount. So we want to be in a world where the verifier says, I'm agnostic. Give me a program, right? And then, Mr. Prover, you say you ran it for 1 billion steps, for a gazillion steps, and that's fine. All I care about is the description of the program. The verifier will need to run in time that is logarithmic in the running time of the program. So there is some dependence, but it is logarithmic, and you can't avoid logarithmic dependence for mathematical reasons. But that's what you want to achieve. You want to be in a world where, with no trusted setup, with no setup at all, trusted or untrusted, the verifier can just come and say, okay, here's a new program. Good. I want to see a proof for it. And the amount of computation from start to end that the verifier does is just logarithmic in the in the running time. Okay, if you're using an error to express a long computation for proving in a Stark, okay, sorry, I answered that. So let's go on to the next question. From the name, it sounds like errors are a more compiler's flavored way of looking at the ZKP problem than the more linear algebraic way of the R1CS style. I would rephrase that and say that errors are a more program-oriented or programming language / compiler-oriented way looking at it. It is still very much a linear algebraic compiler / programming language view, because it is also, an error is also phrased in a very algebraic language. And in R1CS style, so both of them would be algebraic or linear algebraic. None of them is quite linear algebraic because R1CS is already a quadratic, so it's not really linear algebra. But yeah, R1CS, my mental model is that R1CS are a little bit more like, an unrolled chip, right? So like this sort of circuit that we have a bunch of sequence of gates and sort of you run through this thing, even though R1CS constraints allow more, as we said. It doesn't necessarily need to be a linear circuit, but that's how you think of it. And errors are a little bit more resembling a succinct program that talks about a longer computation. Of course, you could write an error that talks about just the circuit. That would probably be pretty inefficient, but you could do that. It's just like, you could write a C code that is the unrolled version of, let's say, running SHA-2 or any other program. But usually you would use a C to write a program that has a loop inside it and does stuff. Okay, how are error in R1CS impacting the construction of proof recursion? That's a very good question. Let's see if I even know the answer off the top of my head. So proof recursion means that you basically have a prover proving that it ran a verifier. That would be level 1 recursion, and it could be more levels. You could have a prover proving that it ran a verifier, and that verifier verified some other prover that verified a prover, and so on and so forth. So that's what we mean by recursion. So you can, since both systems, I mean, both sort of ways of writing things are you can express any computation. You can write them. You can build recursion using R1CS, and you can build recursion using AIRS. I would need to think more about the impact of these things. So I can't answer very well off the top of my head, other than you can use both versions to have you have recursion. Okay, how actually looks like the AIR for R1CS or R1CS of a hash function? That's a very good question, and it really depends what the hash function is. So I can tell you, for instance, that for things that are Stark friendly, for instance, Peterson over a field over which the Stark is arguing was pretty Stark friendly. So the way it would look like would be, maybe I'll go back and just discuss this, because I wanted to talk about how do we actually build programs and so on and so forth. So maybe this will segue into this, and then this will be the last topic for this time. So let's suppose we have some loop that repeats, I don't know, every 64 time steps. And I want to pick a power of 2 for reasons that might become clear later on, but or just, this. So we have some loop. Maybe this is some hash function. For instance, SHA-2 has 64 rounds. So let's imagine some program that has 64 rounds, and we want to hash something. So basically, we have this loop that goes on 64 times, and then so we have maybe this. When we unroll the computation, we're going to have like the state changing 64 times, and each time there's maybe some different round constant or something special that goes on here. And now we get this new input, because maybe it's a hash function, and then it sort of repeats itself for 64 times again, right? And so on and so forth. And maybe this whole thing repeats itself, I don't know, whatever, 2 to the 30 times, because maybe we're computing the hash of a billion, some file of size 1 billion. So we want to run this hash. Takes us 64 steps. Then we take another input. We run it for another 64 steps, and we want this whole thing to run for 2 to the 30, 2 to the 30 iterations. So overall, like the overall t equals 2 to the 30. 64, I think, is 6, right? So 2 to the 36 steps, broken in this way. So, and okay, what we could do always is sort of make it into a circuit and into like an R1CS, right? But actually, I don't want to go there, right? So we don't want to do this. We want to have some succinct representation. And the reason we don't want to do this is if we go that direction, then someone on behalf of the verifier will need to do something with this huge circuit that has 2 to the 36 steps. But we have this program that maybe has 64 lines, and then some code. So this is the program. It has 64 lines, and then some counter that iterates. So iterates whatever, I equals 2 to the 30 steps. So we have this simple program that looks like this. So how are we going to work with it? Now, we are working in a field where we assume that we have a multiplicative group. Multiplicative group. Of size significantly larger then 2 to the 36, and it is so it is a group of power. Its size is a power of 2. So I don't know. Its size maybe is whatever, 2 to the 50. Who cares? Something large, and that's the size of the group. It's, well, let's just assume the size exactly equals 2 to the 50. Why is this useful? Well, it turns out that if we look, I want to talk about succinct representations. So here's something neat. If we look at the polynomial x, to the power 2 to the 50 minus 1. So notice that it has 2 terms, right? It really has 2 terms, right? X to this power minus 1. However, this is the polynomial that vanishes on G. And this is follows from very fundamental theorems about the nature of cyclic groups. I forgot which one is this. Forgot the name of this very famous lemma. Probably someone in the chat group can mention it. But basically, any element of this group, if you raise it or if you multiply it to the order of the group, you'll get the identity, which is exactly what's written here. Good. So that's one thing that you can do. But if you look at x raised to the power 2 to the 20, well, this is a periodic function on G. And furthermore, the interesting part is that, so you can think already, what is its period? So what I mean by periodic is I mean that if you take this function and you basically look at, wait a second, what do I mean by periodic? If we think of G, so we take a generator for G, we think of it as, G to the 0, which is 1. We sort of write it out in the sequence, and then G to the power 1, G to the power 2, all the way up to G to the power 2 to the 50 minus 1. So this is a sequence. And if we sort of write down below here what is f of G to the I, where this is f of x. F of x equals this thing. So what we'll see is that f of G to the I sort of wraps around every 2 to the 30 steps. So there is a certain value that repeats itself every 2 to the 30 steps, and this happens always. And so we get this kind of periodic function, and I think you might see already where we're going, and we also get that sort of h of x, if we define it to be x to the power, so I want to say 2 to the 50. See, this is where not being good with computation of actual numbers is going to cause a problem. I want to have something, that sort of wraps around every 30. Right. So if I here, I know what I want to say. If I look at the function sort of x to the 64 is also periodic. No, I want a function with period 64, so I need need the other way around. I want something that has period 64, so it's going to be x to the 2 to the 50 minus 6, right? So this function has period 64 on G. Oops. So why is all this useful? Well, this is useful because we have this huge computation that is going to be executed for, 64 billion steps. But we can express all kinds of things about it. Various constants need to be repeated, or various steps need to be repeated every 64 steps, but just for 1 billion times. So we can argue about these periodic things using these periodic polynomials that are very succinct. So what we have here, we have succinct periodic succinct polynomials that are periodic functions on the domain that we might care about. And I want to sort of end with this point and say that because we can use, because they exist, these magical succinct periodic functions, we can use them to talk about, something that stops after 2 to the 30 steps, but actually, we know what it is. And one way you might do it, you could start your computation with a counter that is valued at g to the 0, and you could also hard code something that knows the value of g to the power 2 to the 36, and basically you could have some constraint that says, well, whenever so from one time step to the other, I always multiply by g. That's basically one of the constraints I'm looking at. So I'm sort of incrementing my counter, and that's a very succinct constraint. And then you have something that says, well, if my value equals the terminal value, which is g to the power 2 to the 36, then something, I must end my computation. And throughout the computation, you could also argue about certain values that must appear every 64 steps, and so on and so forth. So you can use these periodic functions defined in subgroups that have succinct polynomials to have a succinct representation of programs. And just summing up, the way you get to write succinct programs without unrolling them is to use succinct polynomials that are periodic functions. And such periodic succinct functions correspond to any subgroup in your field. So here we spoke about multiplicative subgroups. For those who are familiar, we could have done this over binary fields, for instance, and then we would also have additive spaces or additive groups that are that you can use them as well. And actually, in early constructions of Starks, that's what we worked with. But you could use the sort of group structure of the field to get succinctness from it. And this is a very powerful idea that we use often in the context of Starks. So now I want to ask again if there are questions. While you're typing questions, I wanna briefly just summarize what are the main topics that we went through. Okay, so and let me sort of just roll back and look at the stuff that we did. So what we said is that we want, for some reason, to write to use polynomials to write programs. And if you're asking yourself, if you just joined, or asking yourself, why would we want to do such a weird thing? The answer to that is given in previous lectures. So now we're just talking about how we're going to write computations using polynomials. And then we sort of said that there are two basic ways to think of computation that are used in the ZKP ecosystem. One is thinking of them as circuits, which leads to R1CS, and the other one is thinking of them as programs, and then you have succinct representations. So in the circuit world, you basically take you want to work with some universal, convenient mega gate that is useful for everything, and that happens to be the type of gate that we like to work with is called R1CS. And the reason historically that R1CS was the choice was that this is the most powerful way to express something that actually is snark friendly and a pairing based snark. And then we talked a little bit about how you can convert things into R1CS. And then we spoke a little bit about airs that allow you to think about algebraic machines. And then when you think of a computation, you think of consecutive states as they evolve, and you just sort of write a system of polynomials that captures the correct transition pairs. How can you move from one state to the other? And you have more freedom as you're looking only at this local transition, And you can have arbitrary degrees, and you're not limited to rank 1 quadratic constraints. So we did a little bit of comparison. And the final thing I spoke about is that the way you take this sort of local state and then get to sort of argue about a very long runtime is to use succinct periodic, succinct polynomials that talk about large structured periodic functions. And those periodic functions, the ones that we understand best are the ones that correspond to subgroups in your field. They could be multiplicative subgroups, they could be additive subgroups. Both of them are useful for various things. So, okay, questions. And while we're at it, other topics that interest you, I'll mention again some of them, and maybe we'll do a poll. Topics that we haven't spoken about. So one thing I want to suggest, so I spoke to so one of the Starkware's scientific advisors also was my venerable PhD advisor, Avi Vigdelson. He's from one of the luminaries and from the early days of interactive proofs. I asked him if he's willing to maybe come and speak and present. So one option is having him, and there are a bunch of others that could sort of join and talk about the early days of interactive proofs and how the field has sort of moved on since then. That's one option, having a little bit more of a story time plus a lecture by one of the founding fathers of the area of proof systems going back to the 80s and 90s. That's one option. Another option is to talk a little bit more about what does zero knowledge mean, right? What is zero knowledge? What do we mean by zero knowledge? What do we mean by an argument of knowledge? How should we think about it? And I don't want to give the cave example that's sort of been used ad nauseum. So something else that would give us a little bit of intuition of what we mean by zero knowledge. And a third topic, which is one that is very dear to my heart, but sort of extremely mathy, is soundness. What do we mean by soundness and how do we analyze soundness in the world of locally testable codes, PCPs, PCPs of proximity, IOPs of proximity, things like that. What do we mean by soundness, and what are the challenges in doing that? So I see three sort of topics, but of course, like the topic for this week was actually suggested by one of you guys. So if you have some other topic and people can poll on it, so that we'll put here a poll, and those are a few of the options that you can use. And here's now I'm going to be answering some of the questions. Okay. Is it correct to think about these as they describe how to verify a computation given the input and output, but not necessarily how to execute it? Yeah, that's a really good question. So, and the answer is you're right. Meaning, all we care about is the fastest way in which we can verify that the computation was done correctly, given the input and the output, and not necessarily how to execute it. Yes, we care less about how it was actually executed. We would like to find the most succinct and efficient way to verify that a certain computation was performed correctly. Definitely, yes, that's the right way to think about it. So when we write proof systems, often we'll say, okay, you know what? Let the prover run this very elaborate computation, but just let us know what the result is. I'll just give one example. Suppose we want to do division, because we need to divide, right? We need to find 1 over, 1 over x, the inverse of something, okay? In all of these proof systems, SNARK, STARKs, R1CS, whatnot, you'll never actually write the sort of sequence of computation that computes 1 over x. And the reason is that that's a polynomial of huge degree, right? In a finite field, 1 over x equals x to the size of the field minus 2, which is really horrible, right? It's like unimaginable. It's as high a degree as you can think of. So instead of that, we say, look, what we want to know is that we want you to sort of guess. You have x, guess some y such that x times y minus 1 equals 0. So that's maybe the most extreme example that is often used. Instead of doing division, we never write a proof system where the prover inside the proof system needs to prove to us that it has done division. We always will check a product instead, because a product is a degree 2 operation, right? X times y equals 1. That means that x and y are inverses. We'll never ask for the computation. Excellent question. Okay. How do you then use an AIR program in a proving system? Can you just make a polynomial commitment of the QIs and then use a generic proving system? Or is there more pre-processing to do? So there are many ways you can use an AIR in different proving systems, and this really depends on what kind of cryptography you want to allow yourself. So for instance, you could do it without any pre-processing at all, right? And that's the way we do it with Starks. Okay, you could have all kinds of table pre-processed in advance, and if you look at papers such as Planck or Fractal, you'll see examples of things where this is what is done. So someone computes in advance a bunch of stuff before you start the computation, and this is used in various ways. So, but there's you don't need to do more pre-processing. I mean, you need to take the program, let's say that was written in C, and somehow convert it into an AIR, right? So there is, but we can think of this as compilation or, okay. I understand that AIR, I'm moving to the next question, could also be used to express constraints over non-consecutive steps, every 8, 4 steps. What are the main differences between AIR for consecutive steps versus non-consecutive steps, if any? So great question, Bobbin, and the answer, there is no big difference between consecutive and bigger jumps, right? So you can, I simplified a lot of things and pushed a lot of stuff under the rug, but you could look ahead, 64 steps or 15 steps, or it doesn't need necessarily to be for 8 steps. It doesn't have to be a power of 2. It could be, some other number. You need inside your computation to look ahead a bunch of steps. You could do that. The effects. So, I mean, every time you need one more entry, I mean, it costs you one more complexity, right? I'm trying to think, where else does it cost you? I don't think it costs you too much. Okay, I'll give a fuller answer. If you go to things like libstark and the original Stark paper that we wrote, they worked over binary fields, and in binary fields, we sort of imitated the multiplicative structure of that you naturally have in prime fields over binary fields. And there, with every jump, so steps, looking ahead 4 steps and 8 steps costs you more in ways I don't want to go into because we haven't discussed what happens over binary fields. Over multiplicative fields, multiplicative groups, if you look at the current time step and the next one, or the current time step and 15 ahead, it doesn't really make a big difference. So the answer is it doesn't make a big difference. Okay, so to remind you, there's a poll. Let's see what, okay, soundness, what do we mean by it? What are the, yeah, okay, I really, really like that. That's something I wanted to speak about from the start. Yeah, definitely. So the next talk will be on the sound of soundness, okay? Please no Waldo. No, I assure you that when I talk about zero knowledge, there's never a Waldo and there's never a cave. That's a topic maybe for the time after that. Zero knowledge with no caves and no Waldos. Free Waldo. Okay, thank you all very much. I'll send a bunch of links for reading. And the topic for next time will be the sound of soundness. I like that topic a lot. Okay. You can send me an email as usual. See you around. Bye.